Hi everyone, this is Chow from Georgia Tech. Today I'm going to share with you our recent work on adversarial Objectness gradient attacks on real-time object detection systems. This is a joint work with my advisor, Professor Ling and collaborators Margaret, Ju-hyun, Emery, Stacey, Wenqi, and Yan-Zhao. In the last decade, deep neural networks have become the dominating technology behind many visual recognition applications. To give a few examples, in self-driving vehicles, we can accurately detect traffic signs within the visual range. Or in the healthcare industry, there is a growing interest in applying neural networks for automatic diagnosis of disease. And also there are many security-critical applications like intruder detection or weapon detection in X-ray machines. These applications are all driven by the same computer vision technique, object detection. And different from image classification, where you can only know a class label of the given image, losing all the fine-grained information, object detection can tell you exactly how many objects are there, where are they, and what are they. So that's why object detection is very popular and useful in many scenarios. To understand how object detection works, let's look at an example with a person holding a stop sign, which is a typical driving scene. To detect the objects on this image, it will be sent to the input layer of the neural network trained to be an object detector and undergone the forward propagation. The object detector will carry out three tasks. It first predicts the existences of the objects, and then the next task is to estimate the bounding box of each detected object. And finally, the last task is to classify what kind of object is enclosed in each bounding box. So at the end, we will get this beautiful result, a person holding a stop sign with high confidence. And the self-driving vehicle can make the decision accordingly. While the advances in deep neural networks offer unlimited opportunities in different areas, like this one, self-driving vehicles, they are very sensitive and vulnerable to adversarial attacks. Recent studies have found that even though deep learning-based image classifiers offer unparalleled accuracy on different challenging competitions, such as ImageNet, they are sensitive to small perturbation to input. Just like this example of an image with a dot, if we send this benign image without any perturbation to the neural network, it can make classification correctly. However, an adversary can generate small and even human imperceptible perturbations to distort the input image. The generated adversarial example can look identical to the benign one, but if we send this to the same classifier, those tiny perturbations will be amplified throughout the forward propagation and become large enough to alter the decision of the classifier. In this case, the image is mislabeled as a cat. Existing object detection systems are driven by neural networks because of the efficiency and also the detection quality compared with traditional feature matching-based techniques. That's why those systems are not an exception and should be vulnerable to adversarial attacks as well. However, in image classification, we know that the adversarial attacks, no matter how sophisticated they can only lead to one outcome, which is misclassification, and the attacks are to generate a perturbation in different ways to push the benign image from one side of the decision boundary of the classifier to another, so that when the perturbed image is being processed by the victim classifier, a different class label will be returned. The situation in object detection is more complicated. To explain this, let me go back to the previous example, detecting objects on an image with a person holding a stop sign. To conduct object detection, three tasks need to be done by the neural network. The first one is the prediction of the object existence, which is actually a binary class classification task, either exists or not exists. The second task is to estimate the bounding box, such as the width and the height. And this is actually a regression task. And finally, the last one is the classification task, determining the class label of the object of each bounding box. So that's why object detection is a multitask learning problem with a combination of both classification and regression objectives. So we know that object detection systems are more sophisticated with 3 tasks covering both classification and regression. Attacking such systems become more challenging because there is no decision boundary to cross, which is leveraged by some attack techniques in the image classification domain to generate the adversarial perturbation. But it also becomes more interesting as well, because what we can do is not limited to just misclassification. The key questions are what kind of malicious behaviors we can impose on the object detection system under attack, and also how to realize them. In this work, we introduce a suite of attacks called TOG, which reveals the adversarial vulnerability of object detection systems. Through TOG attacks, we show that object detection systems can not only be deceived to misdetect with unpredictable errors, but can also be controlled to misbehave purposefully with 3 types of consistent malicious effects. TOG can also be launched as universal perturbation attacks, which are highly efficient and can be done in real time, or adversarial patches, a form of physical attacks with confined visual distortion. Finally, different from existing attack techniques, TOG attacks are designed to be applicable to a wide range of popular detectors, as we do not leverage some specific structures that only exist in some object detection algorithms. TOG is based on the concept of gradient attacks. To understand how it works, let me go through the training process of DNN-based object detectors. Given the training image as input, we send it to a model to be trained. After the forward propagation and generate the output, a loss function will be computed. For object detection, the loss function is more complicated beyond a cross-entropy loss commonly used in classification tasks. As briefly mentioned earlier, it is a multitask learner with 3 goals. The first one is to predict object existence, the second one is to estimate the bounding box of the objects, and the last task is to classify objects. That's why the loss function in object detection consists of 3 components. Each of them corresponds to one specific task aiming to minimize the prediction errors. During the training process of a neural network, the gradients will be computed with respect to the model parameters theta, and a backward propagation will be conducted to update the model parameters. The input image will not be changed in the training process, only model weights will be iteratively modified. TOG also goes through the same procedure, but in this case, we send the image to be perturbed to a trained object detector, which is the victim to be attacked, and compute an adversarial loss. The key challenge in attacking object detection systems is the design of such an adversarial loss, and TOG exploits different combinations of the 3 learning tasks in object detection to define a set of adversarial loss functions with different attack effects. With the adversarial loss, gradients are computed with respect to the input image X, and iterative update is done on the input image while the model parameters remain unchanged. TOG contains a set of 4 adversarial loss functions, and each of them corresponds to one attack effect. They can be broadly classified into untargeted random attack and also targeted specificity attacks. But before talking about each attack, let's look at the 2 example images that will be used for explanation. Given benign inputs, both images can be perfectly detected by the detector, just like the person and the dog in the first row. The first attack is the TOG untargeted random attack. The objective is to generate adversarial examples that can fool the victim to misdetect with any kinds of errors. For instance, given adversarial example, the victim detector misdetects multiple bounding boxes of person in the first image. This attack can behave differently across different images, even on the same victim detector. Just like the second image, both cats are missing given the adversarial example. The next 3 attacks are targeted, meaning that we also want to control the behavior of the misdetection. And the first one is the TOG vanishing attack. which is designed to fool the objectness component of the victim such that it has no capability to recognize any object. From an information retrieval perspective, this attack significantly reduces the recall of the victim, just like no objects can be recognized in both images. The second targeted attack is the fabrication attack, which deceives the victim to recognize additional false objects. And this is equivalent to reducing the precision of the victim because those objects detected by the victim are unlikely to be real. Finally, the third one is the TOG mislabeling. It is much more aggressive because it deceives the victim to mislabel the detected objects, but the perturbation should not affect the objectness and the bounding box component. For example, the person in the first image is mislabeled as a dog with the same bounding box, and also the dog is mislabeled as a cat. These are the four TOG attacks that are capable of deceiving object detection systems to misbehave with either unpredictable errors or consistent malicious effect. One way to realize TOG is to tailor an adversarial perturbation using the adversarial loss functions for each input image. The perturbation is fine-tuned iteratively until the goal is reached, such as successfully fooling the victim to mislabel the object while keeping the same bounding box. We also extend TOG to two additional forms, and the first one is called universal perturbation. Instead of optimizing an adversarial perturbation per input, we train the same perturbation to fool the victim by using a training dataset. Once the universal perturbation is obtained, we can then apply the same distortion on every image received by the object detection system without additional optimization. So far, the two forms of realization are both allowed to perturb the entire image digitally. The third form is called adversarial patch attacks, which trains a small patch offline such that when an object is attached with such a patch filled with malicious patterns, the object detector will misbehave. Different from the first two approaches, the carefully generated adversarial patch may also be used physically by printing the patch and attaching it to the object. For example, a person can attach an adversarial patch to bypass the smart surveillance system, or someone can put a sticker with an adversarial pattern on a stop sign to fool the traffic sign detector and potentially lead to accidents. We have conducted extensive experiments on three benchmark datasets, including VOC, COCO, and INRIA. To evaluate TOG on different types of detectors, we consider both YOLO v3, SSD, and faster RCNN with different configurations in neural architectures and also input resolutions. That's why we have 5 detectors in the collection. We also compare TOG with existing attack techniques, but in this presentation, I will highlight the results of TOG on VOC and INRIA datasets. We first discuss the performance of TOG attack with an untargeted objective. In the object detection domain, we use the mean average precision or MAP to quantify the detection quality of an object detector. This metric considers both precision, recall, and the confidence of detected objects. Given benign inputs where no malicious perturbations are introduced, the 5 detectors can offer high-quality detection results with over 67% MAP. And the latest algorithm in the collection, which is YOLO v3 with a darknet architecture, can even reach 83%. This high-quality detection is disabled by our TOG attack. By adding just human imperceptible perturbations, like those examples I showed earlier, to the benign input images, the victim detectors can only reach less than 3% MAP, meaning that there is no detection capability at all, and we shouldn't trust the results returned by the object detection system. For TOG with targeted objectives, the reduction of MAP is equally detrimental, but we can even control the behavior of those victims. Let's understand the capability of the TOG targeted attacks from a different perspective. We measure the total number of objects detected by the detectors on the entire test set with about 5,000 images. Given benign inputs, those 5 detectors can recognize about 10,000 objects. But given adversarial examples generated by the TOG vanishing attack, the detectors are no longer capable of retrieving objects from the input images. For example, the YOLO v3 detector with a MobiNet architecture can only detect 8 objects from those 5,000 images. And for TOG fabrication attacks, they can effectively fool the victim to return 10 times more objects, meaning that a large number of false objects are mistakenly recognized. Interestingly, the mislabeling attack does not have a significant impact on the number of detected objects, and this is a desired property from an adversary perspective because the goal is to fool the victim to mislabel existing objects while not introducing additional ones or making any object vanish. We compared the objects detected on benign and adversarial examples and found that under TOG mislabeling attack, over 70% of the objects can be purposefully mislabeled with the same bounding box, and this reveals the effectiveness of TOG in not only fooling the victim's classification component and also keeping the other 2 tasks, which are the objectness prediction and also the bounding box estimation to be unaffected. Just like the example images on this slide, the cat becomes a motorbike with 99% confidence and a correct bounding box. After showing TOG's capability in bringing down the detection quality and launching attacks with a consistent and malicious effect, in the next few slides, I will demonstrate TOG as a universal perturbation attack or adversarial patch attack. We train a universal perturbation using the TOG vanishing formulation, and at the same time, we have prepared a 10-minute driving video where the object detector can recognize around 400,000 objects. By applying the same universal perturbation on every image frame from this video, the same detector can only detect 54 objects on the entire 10-minute adversarial video. This form of attack is particularly detrimental to systems requiring real-time responses because there is no per-input optimization involved. As indicated by the 2 yellow circles, the frame per second processed by the system is just slightly reduced from 41 to 39. Finally, to evaluate TOG as adversarial patch attacks, we use the in-real dataset and train 2 types of patches with the TOG formulation. First of all, we use the TOG vanishing objective to generate an adversarial patch to be attached to every person in the dataset. We also include a baseline with a patch filled with random noise. This baseline can only make 1% of people vanish from the victim's detection, but the TOG patch is much more effective with a success rate of 97%. For the second type of adversarial patches, we trained 19 different patches with the goal of deceiving the victim to mislabel the person with the patch to 19 different classes. For example, on this slide, the adversarial patch is to fool the model to detect any person with the patch as a chair. And we can observe that the success rate can be close to 100%. So even if we just use a confined visual distortion like this, TOG can still deceive the victim and even preserve the targeted attack effect. This kind of adversarial patches can be combined with regularization techniques to generate printable patches, which can become a form of physical attack. In this paper, we have presented a suite of attacks called TOG to deceive object detection systems with not only unpredictable random effect, but also 3 types of targeted attacks, forcing the victim detector to misbehave with a consistent behavior. We have also developed effective mitigation algorithms to counter TOG as well as other existing attacks on object detection systems. More details including the latest results can be found in our paper and also my homepage as well as the open source project of TOG on GitHub. I hope you enjoyed this presentation. Thank you so much.